All right, students, we're going to jump into chapter 5, which is all about stereochemistry. Now, we introduced the idea of stereoisomers, or, well, isomers in general, right? We talked about constitutional isomers, and now we're going to go a little bit deeper into this idea of stereoisomers. This is actually really, really important, even though it's going to seem super trivial. When you look at these sorts of things in biology, they become of tremendous importance. So let's introduce the main idea that we're going to be talking about this chapter, and this is the idea of chirality. Okay, so chirality refers to handedness, essentially. So the idea is you have two objects, or you have an object, and its mirror image is not superimposable on the original image no matter how you rotate it. For example, a right-handed glove, there's no way you can rotate a right-handed glove to fit your left hand, right? So that's the best way to think of it is this idea of handedness, okay? So, as you'll see, we do actually think about it in terms of, and one of the easy ways to determine chirality is to actually use your hands. So, a chiral molecule has this property of having its mirror image different from itself. The idea, again, is non-superimposable. There's no way I can rotate this image, right? Not flipping it over, but rotate this image and have it perfectly superimposed on the original image. Okay? An achiral object, we're going to talk about molecules, but any object could be achiral, right? The mirror image is identical. Okay, I can overlay the picture of the chair on the chair, and it'll fit perfectly. Okay, so stereoisomers, right? We talked about cis and trans, but there are different classes of stereoisomers that have different differentiations, right? There's a lot of different categories, and we'll look at a breakdown of each different category to help you categorize molecules as, you know, achiral or chiral or whatever, but here's a term that's important: an enantiomer. Okay, an enantiomer is a compound that is a non-superimposable mirror image. So this molecule you're looking at, okay, the way the atoms are arranged, you cannot rotate the molecule on the right to get the molecule on the left. So if you were to flip it, right, the bromine would be going away from you and the hydrogen would be coming towards you. So even though these are the same molecule, right, with the same connectivity, because the bromine is going towards you on in one molecule and away from you in the other molecule, these are called enantiomers. Now they are the same molecule, essentially, right? But they will react differently in certain biological instances. So chirality really doesn't matter a lot for chemistry lab work, which you'll see why. But in biology, chirality is super, 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 super important. Okay, so any chiral carbon atom, which is also called an asymmetric carbon atom, is any carbon atom that's bonded to 4 different groups. Okay, so it's an sp3 carbon, it's tetrahedral, and it's bonded to 4 separate groups, right? So if it's bonded to 2 of the same group, whether that be 2 hydrogens or 2 chlorines or 2 ethanes, right? If any carbon is attached to 2 of the same group, it is a symmetric carbon. It is not a chiral carbon. Okay, it has to be attached to 4 unique things, because that's the only way that the mirror image is an enantiomer. Okay. So every asymmetric carbon is what's called a stereocenter or a chirality center. Okay, so a stereocenter, as the definition is here, is any atom in which the interchange of 2 groups gives a stereoisomer. So the ones that we're most concerned with are asymmetric carbons and carbon-carbon double bonds, right? Cis-trans. So now cis-trans is not chiral. Okay, chiral specifically refers to these asymmetric carbons. Okay, so stereocenters is a broader term than chiral centers, right? So, okay, so it's using nitrogen as a chiral center as well. We're really not going to look at a whole lot of chiral nitrogens, so don't worry about that too much. But the idea is these are the asymmetric carbon and the nitrogen there are chiral centers, and they're all, including the double bond, stereo centers. Okay? So an achiral compound is any compound in which you can rotate it and get the same compound, right? So in this case, right, the carbon has 3 things attached to it. So let's just assign those things other than numbers, right? So let's say this is a bromine, and this is a chlorine, and these 2 are hydrogen. Okay? So bromine, chlorine. As you can see, there's actually a plane of symmetry here on which the hydrogen is the same on both sides. So that is an easy way to tell whether it's an achiral compound, right? If it has an internal plane of symmetry. Okay, so yeah, if you view it at a certain angle, right, you can have it be the same on either side. So that is achiral, right? If it was different things, okay, so if this was, let's say this was a chlorine, this was a bromine, this was a fluorine, and this was an iodine, okay, iodine. This would be the fluorine, this would be chlorine, this would be bromine, right? Now it's not the same on both sides, so that would be chiral. So really the easiest way to think about it is, does it have the same thing, it does have 2 of the same thing attached to one carbon, then it's achiral. But you can also think about it in terms of, does it have a plane of symmetry through the central molecule? If yes, then it's achiral. Okay? Cyclic compounds are achiral if they're cis, but they can be chiral if they're trans. Okay? So a cis cyclic compound, right? As you can see, if you cut it down the middle, it's symmetrical on both sides, right? If it's trans, right, one's up, one's down, then it doesn't. So then it can be chiral. So that's the one part where it might be a little bit tricky. So if you look at the trans compound, right, these are not the same, right? You flip it, these are not the same, so these are enantiomers. So the cis compound will be achiral, and the trans compound would be chiral. Okay, so that's the ring. Again, ring structures add a layer of complication, but this is kind of the one real exception you need to be looking for. Okay, so these chiral compounds, right, they have handedness. Okay, so if you look at them, okay, here's your chiral carbon. All right, so this is a chiral carbon, chiral center, and it can be one of 2 ways. Right? This is the mirror image, non-superimposable. This is alanine, so an amino acid, and this is how it occurs in nature. And this is the opposite, what we would call handedness, right? So we would get the same name under IUPAC, right? 2-aminopropanoic acid. But this gets metabolized by the body, this gets discarded. So we use these, what we call configurations, absolute configurations, to tell you this is how it's laid out in space, similar to the way you would say cis and trans. Okay, R and S are similar to cis and trans in that it's the same compound, like formulaically, like the same formula, right? The same connectivity, but the arrangement in space is different. So we use R and S to indicate those the handedness. And R is right hand, S is left hand is the easiest way to think about it. So R for right, and then S is the other one, which is left. So this is called the Kahn-Ingold Prelog convention. You don't need to remember that. But the idea is any chiral carbon can have 2 possible configurations. And based on that configuration, it is designated R or S, each asymmetric carbon. So you can have multiple chiral centers in a single molecule. Okay? And this convention is how you go about doing this. And I mentioned priorities, but now we're going to actually look at priorities. So the first step is to assign priority. And this is the same for numbering, right? This priority list, what you will also use for numbering. So if you have 2 equal things, let's say, okay, so let's say you have which carbon is carbon 2, right? It's between bromine and chlorine. So higher atomic numbers receive higher priorities, so you would say, all right, that would be 2 bromo, 4 chloro. Okay, so this idea of priority stretches into numbering carbons, just so you know. So that's helpful for nomenclature as well. Okay, So highest priority goes to higher atomic numbers. So it goes iodine, bromine, chlorine, sulfur, fluorine, oxygen, then nitrogen, then carbon-13, carbon-12. This, you're probably not going to see this, right? Lithium, hydrogen. So in general, you just assign priority in terms of atomic weight. That's the easiest way to do it. Okay? So if we were to look at this carbon, right? Fluorine is more important than nitrogen. Nitrogen is more important than carbon. Carbon is more important than hydrogen, right? It's all relative to what's attached immediately to the carbon. So we would call fluorine 1, we call nitrogen 2, we call this carbon 3, and we call this hydrogen 4. Now, almost always, you're going to have a hydrogen, and that's going to be the fourth. So almost always, you're going to ignore that. So then we say breaking ties. Okay, so if you have a tie, then you look at the next atom over. Okay? So, right, if we look here, if this, so in other words, if you have R3, and then this, and this is your R prime, okay? And you're trying to consider priority, right? If this is what you're looking at, if it's a carbon then a bromine, well, that's more important than a carbon. So, okay, let's try this out. Okay, so we're looking at this carbon. Okay, it's got 4 different things attached to it, but the first thing is all carbon. So we determine, okay, what's the most important carbon? Well, we go carbon, and then the next thing over is a bromine. Okay, so that's the most important thing. Because this is a carbon, then a chlorine. So bromine, then chlorine. So carbon, carbon, and then a bunch of other carbons, 3 carbons. Okay, so that's 3. And carbon, 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 bromine. Right, so this is carbon with 2 carbons. This is carbon with 3 carbons. So even though this one, the next thing on here is a bromine, and that you would think they're given priority, it's just the next step over. Okay, so we go 1 step over, carbon. Then we go 2 steps over, carbon, carbon, hydrogen, carbon, carbon, carbon. So this one becomes more important. Okay, and chains don't matter unless you're going. So if you were to see this chain, right, you go carbon. And the next thing, carbon, and the next thing, bromine, carbon, so then that would assign priority, okay? So this is just going to take some practice. Again, everything's open book, so you can have that priority list open in front of you. If you can't remember it, that's fine, okay? In multiple bonds, treat double and triple bonds as if each were bonded to a separate atom, okay? So if you have a double bond if you need to look at priority over a double bond, this is how you do it. Okay, you just consider it as though this were the case. So right, it's carbon double bond carbon. So you consider it as though it was carbon carbon. Right, both of these carbons were attached to one other carbon. Okay, so if this is the thing you're looking at the chirality of, and you have to go 2 over, you would say, all right, this carbon is attached to 2 carbons. That's how you would do it. And this carbon is attached to 2 nitrogens, and this carbon is attached to 3 carbons. Right, so that's the general idea of how you determine priority for a double bond, for a triple bond. Okay. Step 2, and this is the hardest part. Okay, so this is by far the hardest thing to do because it requires you to think about things in 3D space, something I'm terrible at. So thankfully, this is because we're only working with one thing at a time. It makes it a little bit easier. Okay, so you're going to put the hydrogen in the back. Okay, so that you have 3 things pointing out towards you. And then you're going to determine, is the order of the things clockwise or counterclockwise? If it's clockwise, okay, so you put the hydrogen in the back, and then you go 1, 2, 3, okay, in a clockwise rotation, so that's R. And if it goes 1, 2, 3 in a counterclockwise or anti-clockwise if you're British, that's S. All right? That is the idea. Okay, so if we look at alanine, and we say, okay, what is it attached to? It's attached to 2 carbons, a nitrogen, and a hydrogen. Well, hydrogen is always going to take the lowest priority, so we get that 4. Nitrogen's the highest, so we give that a 1. Then we say carbon, carbon, that's a tie. What's the next thing it's attached to? Hydrogen, oxygen. Oxygen is more priority than hydrogen, so this carbon gets priority 2. This carbon gets priority 3. So then we have all 4, and we need to say, all right, let's put this hydrogen in the back. Okay, so if we do that, right, it'll look like this. And the hydrogen's like going off in the back there. Okay. Okay. 1, 2, 3. Okay. Counterclockwise, so that becomes S. Okay. So you can also in this drawing you can see it that you go from 1 to 2 to 3 this way because that's pointing back. So you go this way. That's counterclockwise. Okay. So that makes it S. All right. So you always want to put, so in this case, so here's where it gets tricky, right? Here, the hydrogen is pointing towards me. Okay, so what do I need to do? Well, I need to rotate this so that the hydrogen's in the back. So if I rotate this to the back, then this is going to come over here, right? I'm going to flip it. Basically, I'm going to flip it down. Okay, so if I flip it down, right? It tells you, right? Okay, so if you're going to, when rotating, put the lowest priority group in the back, keep one group in place and rotate the other 3. So if I keep, so in this case, they're keeping this group in place. They're saying this is going to stay here. Okay. Then what they're doing is they're taking 1, moving it to 4, 4 moving it to 3, and 3 moving it to 1. Okay. So they're rotating the positions that way. And they get, so now 1 is the one coming towards you. 4 is the hydrogen that's going in the back. That's good. And then the ethyl group is coming up. Okay. So then we say, all right, 1, 2, 3, clockwise rotation, that's R. Okay, so that's the best thing to do. And you can rotate this any way you see fit, okay? So you want this hydrogen to go in the back. So what if the hydrogen was over here? Well, okay, so then you maybe hold this one forward and rotate it around that way. Or hold this one and rotate it that way, right? It'll depend on where the hydrogen is, how you want to rotate it. But this idea of keeping it, basically you're going to keep this one and then swap the positions over to make sure the hydrogen goes to that back position. Okay? So that's probably the easiest way to do it. Okay? Don't know what that example continued is. Not sure what's going on there. Okay. So draw the enantiomers of 1,3-dibromobutane and label them as R and S. Making a model, blah, blah, blah. If you happen to have a molecular modeling kit, it's very useful, especially for chirality. It's like the most useful thing for chirality. So if you have one available to you, I highly recommend you play around with it. Okay, so this carbon, 2 hydrogens, not asymmetric. 2 hydrogens, not asymmetric. Here, I've got 1 carbon, a carbon chain, and a bromine. Okay, so let's assign some priority. So we know that the bromine is 1. We know that this is going to be 2 because if we look, carbon, okay, that's a tie. Then we go to the next thing, carbon, hydrogen, so this is 2. And then this is 3. And the hydrogen's obviously 4, so it doesn't matter. Okay? So there are 2 possible ways for this to be oriented, right? You can have either, right, if we put the hydrogen in the back, either it can be R or it can be S. Now you notice the switch between R and S, I'm switching 2 groups and keeping one the same. Okay? So I'm just flip-flopping, right? Because if I rotated all the groups, then I wouldn't have done anything. Okay? So there's 2 possible ways for it to go. It can be R or it can be S. And, right, we draw the mirror plane. This is a mirror image that is non-superimposable. Okay? In cyclic compounds, again, it's a little harder, but so if we look at these 2 carbons, they're the same. And then if we look at the next 2 carbons, right, this one goes, so we got carbon, carbon, tie. Move on to the next one. Carbon, carbon, tie. What's the next highest priority? Well, it's carbon, and then it's oxygen. So this carbon is going to be a higher priority than this carbon. Okay? So why is this one 1, you might ask? Because if we go here, carbon, and then how many carbons is this attached to? 1 other one. 1 other one. How many carbons is this attached to? 2 other ones. So the one with the most priority, you look at everything attached to it and to determine priority. Okay, so it kind of shows you this here. I don't know if I think about it this way, but that might be helpful for you to think about it in those terms. Okay, so enantiomers, they have the same physical properties. Okay, they have the same physical properties. So again, in like a chemical context, in a lab context, you don't need to separate enantiomers. Okay, it doesn't matter. They're going to react the same. The exception is when it's interacting with another chiral molecule. So enzymes are super important for this. Enzymes and biological receptors. Okay, they are designed to only accept one-handedness, one chirality. So it either will completely ignore the other one, or the other one will have unwanted effects. For example, the thalidomide. You may have heard of this. The thalidomide was developed in the 1950s as a morning sickness suppression drug. And when they created it, they did not realize that it has two enantiomers. One of those enantiomers cures morning sickness, as intended. The other enantiomer causes horrible birth defects. They did not know this at the time, and they did not realize that when they made it in the lab, they were making a 50-50 mixture of both enantiomers. So a lot of people got sick from that, and it wasn't until later they understood that we're making this compound, and this very small thing, this idea of, basically, so you swap to the position of two things in space, and that makes all the difference in the world. Okay? So chirality really comes into play. It does a little bit in some advanced chemistry. It'll come into play, but really it comes into play in biology. Okay. Now, the main way to tell the difference between the enantiomers is they actually rotate light in different directions. Okay. So some of you might be familiar with the idea of polarizing light. A lot of people might have sunglasses that are polarized. Basically, what it does is light is, scatters off of surfaces, and so the light that comes into your eyes is coming from all different angles. So what polarized glasses do, or polarized filters do, is they basically make it so that only one light can only come in from the forward direction. So it cuts out the wavelength, the light that's coming in from weird angles. That's why it reduces glare, because the glare is coming at funky angles. So it basically just blocks that light from coming in. So if you hit an enantiomer, a pure enantiomer, R or S, with polarized light, it will rotate it in a specific direction. Now, that direction does not correspond with R or S. In other words, it's not that all R molecules rotate one way and all S molecules rotate another way. One of the molecules, R or S, will rotate one way. One of the molecules, R or S, will rotate the other way. So basically, you get a rotation of degrees, and this can be positive or negative. Okay? And we call this dextrorotary, meaning to the right, and levorotary, meaning to the left. This is where these designations of D and L, which if you've seen ingredient lists and they've added L-alanine or D-glucose, right? This is where those come from. These are not related to R and S, okay? Depending on the compound, R could be dextrorotary and S could be levorotary, and then in a different compound, S could be dextrorotary and R could be levorotary, okay? They will always rotate in opposite directions. That's always the case, but R is not always D and S is not always L. Okay, they could be either. So we call these, we call that the R and S. We call that absolute configuration because it has to do with the assignment of priority and the measurement in space. Whereas this measured rotation is this experimentally determined rotation is not related to whether it's R or S. So you might see the designations D and L. They added L-glutamine. This is what it means. Okay. So, and we're not calculating any of this. So specific rotation is basically you can calculate the rotation, and you can do some things with this. I'm gonna skip this. Right. So this is what makes it important. So R epinephrine, which is what you normally get, goes to the active site as the active site is laid out in your enzymes. Okay. S epinephrine, as you can see, it doesn't fit in the enzyme's active site. So it's not completely a lock and key method. If you go into biology, you'll know what I mean. But you can think of it, at our level, we can think of it as the enzyme is a lock and the compound is a key. So if the key's rotating the wrong way, it's not going to fit. Okay? Just like a right-handed screw, like a right-handed screw on a bottle cap will screw onto a cap, but the left-handed screw on a bottle cap won't. It's the same idea. So when you have a 50-50 mixture of two enantiomers, this is called racemic. Now, almost all of the reactions in the lab that we do that create enantiomers will give you a racemic mixture, or a lot of them will. And you'll see in the next chapter. There are some that are stereospecific, and there's some that are not stereospecific, and will give you a racemic mixture. Okay, so if you have equal quantities of, let's say, R and S, or D and L, or however you want to say it, and so here you see S plus butanol, R minus butanol. What that's telling you is that it's S, D butanol, R, L butanol, because that's how it rotates. But if you look at this, R, L epinephrine, S, D epinephrine. Okay, so that's just showing you that the D and the L, the plus and the minus, are not related to R and S. The R and S is what we call absolute configuration. So the enantiomers will have no rotation, right? Because you got plus 13.5 from the one and minus 13.5 from another, so that's going to equal 0. So if you have a racemic mixture, you will get a 50-50 form, a optically inactive mixture. So, for example, if you add, and we're going to look at some reactions, right? So if you basically hydrogenate a carbonyl, right? You can add hydrogen to a carbonyl. It turns it into an alcohol. That hydrogen, right? It's floating around in 3D space. Can come from the top or it can come from the bottom. When it comes from the top, you get one configuration. If it comes from the bottom, you get another configuration. So since it's essentially a 50-50 chance of coming from top or bottom, you get a 50-50 mixture of products. So optical purity or enantiomeric excess is basically saying you got more of this rotation than the other rotation, which means you got more of this handedness than the other handedness. And we're not going to do the calculation. We're just going to move on. Okay. So conformers, remember conformers, and so if you have conformers and you can go between two different chiral conformers, then it's not chiral. So if we look at this, right, remember conformers are like the axial equatorial stuff. Okay. So the chair conformations are not interconvertible, right? Let me start. They're non-superimposable, but you flip from one to the other so fast that essentially any sample you would pick would be racemic. So you don't consider this. This is like an exception, even though this is like technically chiral on a molecular level. On a realistic, like a practical level, it's essentially non-chiral, because you're flipping back and forth so fast that when you would have a chance to look at the chirality, it'll have flipped to the other conformer. So non-mobile conformers, meaning you can't change it. Okay, so something like this, where you have two rings that are perpendicular to each other. If you try to rotate that, then your substituents are going to crash into each other. Okay, so even though there is a conformation that's achiral, because you can't access that, you are considered a chiral compound. Now, these are fringe cases, so I don't want you to worry about this too much. It's just important to understand that you could run into something that you could run into a ring system that is chiral, but because it interconverts so fast, it's essentially achiral. And you can also run into a conformer that could be achiral, but due to steric constraints, it's going to be chiral. So those two staggered formations, since you can't rotate around that bond because the bromines and the iodides will bump into each other, those are essentially, for all intents and purposes, are chiral, even though, right, you could conceive of, if the bond were longer, they could just freely rotate. So there are some minor exceptions. I don't want you to get too worried about those. Focus more on the individual carbons, the asymmetric carbons. That's what's really going to be important. Okay, so allenes are chiral carbons that are chiral compounds that don't have a chiral carbon. Okay, so the way this works is you have carbon, double bond, carbon, double bond, carbon, and what you're doing is you're looking at the carbons on the end. Okay, so this is what it looks like. Oops. And this is a rare case. But basically, you're considering this whole thing as one chiral center. Okay, this whole big block is one chiral center. So you look at your constituents as, right, 1, 2, 3, 4. Even though these are the same things, you end up with a rotation of 90 degrees. So this is a very rare case where this is chiral, even though it has equivalent things, even though it doesn't have any chiral carbons. So this is the exception of the exceptions. You're not going to see this a whole lot. Just know that if you see the structure, carbon, double bond carbon, that's a chiral center. So now we need to look at something called Fischer projections. So Fischer projections are basically the easiest way to write out chiral carbons. So what you do is you're basically looking at the 3D structure in such a way that you have two things coming up and two things going back. Okay, so you're viewing it so that these two things are coming towards you, and these two things are going away from you. Okay, so the away from you goes on the vertical plane, and the towards you goes on the horizontal plane. Okay, and you basically draw that as a flat structure. Okay, so here's my chiral carbon, and here are the things that are attached to it. This is by far the best way to look at chirality. It's the easiest way to look at chirality. It does take practice to be able to convert from a Lewis structure to a Fischer projection, but generally we're going to start with the Fischer projection as it's just easier. Okay, so here's another way of thinking about it. Okay, so I'm looking down. So carbons 1 and 4, so substituents 1 and 4 are pointing up at me, and 2 and 3 are going away from me. 2 and 3 are oriented vertically, 1 and 4 are oriented horizontally, and then you get your Fischer projection. Okay, so here's how you do this. Carbon chain goes on the vertical line, right? Highest oxidized carbon is at the top. Rotation of 180 degrees in plane doesn't change the molecule. So if you flip it upside down, it's still the same molecule. Rotation of 90 degrees is not allowed. So you can't go from, so if you take this and you flip it 180 degrees, okay? You go to CH3 on top, OH over here, H over here, and COOH on bottom. Okay, that if you were to reorient that and you were to check it, that would not change anything. Sorry if you hear people yelling in the background. But if you rotate it, if you were to rotate this 90 degrees and you were to do it like this, you're not allowed to do that. So you can do this, that's fine, but you can't do that. All right, but generally you want the most oxidized carbon on top, which is not oxygen, it's carbon. You should have carbon on top and a carbon on the bottom if possible. Okay, so you rotate 180 degrees, that's no problem because you didn't change anything. You rotate 90 degrees, and now you've created a problem because that's not the same molecule. It's an enantiomer, right? Because you flipped front and back, front and back. Okay, so you can go 180, but you can't go 90. So let's look at glyceraldehyde. Okay, so glyceraldehyde, You ignore the hydrogen. You ignore the hydrogen, and because the hydrogens always end up on the sides, and this is where it gets tricky. This is where it gets tricky. Because the hydrogens are pointing towards you instead of away from you, the rotation is reversed. So remember, if the hydrogen's pointing away from you, then going clockwise gives you R. So now the hydrogen is pointing towards you, so the clockwise gives you S. So for a Fisher projection, and this is for the part that wrinkles your brain, in a Fisher projection, the rotations are reversed. And only in a Fisher projection. Counterclockwise is R, clockwise is S, in a Fisher projection only. Okay? And Fisher projections are super useful because they let you find your enantiomers, they let you look at mirror planes, right? And they let you determine chirality of multiple chiral centers. So we look at this. Okay? We say, all right, so this is 1, this is 2, and this is 3. Okay? For this carbon, this is 1, this is 2, and this is 3. Okay? So for this carbon, 1, 2, 3. That's S. This carbon, 1, 2, 3. That's also S. So this is SS. Okay? So these both count clockwise, and so they both end up being S. The Fisher projections are really, really useful for determining multiple stereocenters. Because if not, if you try to draw the multiple stereocenters in space, it gets real confusing real fast. Okay, we're going to come back to Fisher projections. There's another designation for Fisher projection that's super important that we need to look at. Okay, so diastereomers, we talked about this. This is cis and trans. These are not mirror images, so they're not enantiomers. They're called diastereomers. Okay, so enantiomers are specifically non-superimposable mirror images, and diastereomers are specifically stereoisomers that are not mirror images. Okay, and we talked about cis-trans on ring systems. I'm not going to go back over this in great detail, but remember, you can have cis-trans in a ring as well because that single bond is locked in place because it's in a ring. Okay, so diastereomers. So if you have multiple chiral carbons, you're going to have diastereomers and you're going to have enantiomers within the same thing. Okay, so if you look at this, you've got two chiral centers, two different chiral centers, and so there's 4 possible configurations. Okay, you can have SR, RS, SS, or RR. Right? They can be different. They can be different 2 different ways. They can be opposites. Right, 1S, 1R in 2 different configurations, or they can be both the same, right? Again, in 2 different configurations. So these are not mirror images, even though they're isomers of each other. So these are diastereomers. Okay, so when you have 2 or more chiral compounds, you have enantiomers, diastereomers, and mesoisomers. Now, mesoisomers are a unique classification, which we'll get into. But generally, you're looking for the enantiomers, which are the opposite configurations, and diastereomers, which are non-mirror images but are stereoisomers. Okay, and meso compounds have internal mirror planes. We'll talk about that. So, in general, the maximum number of isomers is going to be 2 to the n, where n is the number of chiral carbons. So, if you have 2 chiral carbons, you'll have 4 enantiomers. And obviously, the more enantiomers you have, if you have 3 chiral carbons, there's 8 enantiomers, and it goes up exponentially. So we're not going to deal with things where it has 1 trillion carbons, chiral carbons, because it gets to be a pain in the butt. So, right, if we look at that compound, okay, that if we were to go back to that compound, and we looked at 2R, 3R, 2S, 3S, those would be enantiomers, right, because those would be mirror images, and the 2R, 3S and 2S, 3R would be mirror images. But the 2S, 3S and the 2R, 3S, right, so this is, let me go back to pull it up. Okay, so, right, so this is the, now I'm not gonna draw these correctly, but this is the idea. Okay, so if you have something like this, right, or so these are enantiomers, and these are enantiomers because they're non-superimposable mirror images of each other. Then if you have right, these are enantiomers, but these two, any pair of these two, or this guy and that guy, those are not mirror images. Okay, so these are not in the right order. Okay, so don't think, oh, 2R3R means they're on the same side. That actually usually means this is probably the 2R3R, and that's the 2S3S, right? So I probably have those out of order, so ignore that. But this is the idea. These are the 4 enantiomers you have. These 2 are enantiomers. These 2 are enantiomers. These 2 are diastereomers. These 2 are diastereomers. Those 2 are diastereomers, okay? So here's your flow chart of isomers. So you have constitutional isomers, which are the structural ones, and you have stereoisomers, which are the arrangement in space. Among stereoisomers, you have enantiomers, which are the non-superimposable mirror images, and you have diastereomers, which are not mirror images. Okay, so in diastereomers, you have cis-trans isomers, or geometric isomers, which includes double bonds and rings, and then you have diastereomers that are formed from 2 or more chiral centers. So mesocompounds are a special case where you have an internal plane of symmetry. Okay? So if you have 2 chiral compounds and they have identical constituents, then at some point one of those things is going to have an internal mirror plane. So even though these are 2 chiral centers, this compound is not chiral because it has an internal plane of symmetry. So I can rotate this 180 degrees and it's the same compound. So this is not chiral. This is not chiral, right? Think about ring structures. So those are called mesocompounds. They're achiral compounds, even though they have chiral centers. Okay, so the absolute configuration is that R and S, and the relative configuration would be that D and L. Okay, so if you have a mesocompound, you don't have the 2N rule, because you're going to have 2 compounds that are the same. So in this case, right? Okay, so you have RR and SS, and you have RS and SR. Now RS and SR are the same compound. Now if you replace this with a chlorine, suddenly that's not the case because you don't have this internal plane of symmetry. Okay, so mesocompounds will only happen if you have identical substituents on adjacent carbons. Okay, so diastereomers have different physical properties. Okay, so like trans and cis compounds will have different chemical properties because they have different moments of polarity, but enantiomers will not. Enantiomers really only react with different chiral molecules. So enantiomers are really hard to separate. Diastereomers are easy to separate. So if we think about a diastereomer, right, trans-butene or cis-butene, okay, they have different dipole moments. So they have different boiling points. So you can separate these by distillation. Now this is a mild example. There are some examples. If you replace those both with chlorine, then you'd have a really big difference in boiling point, right? The cis would be a much higher boiling point than the trans. If you think about mesocompounds as well, right? Because these are diastereomers, so you notice there's a very large difference in melting point. So you could separate these by melting point. The R and S configurations, or I guess that they call this plus and minus. So, but the enantiomers of this compound have essentially the same melting point. So then, how do you separate them? It's tricky, and this is one of the reasons why medicine is so hard, because it's really easy to make this compound, but I get a 50-50 mixture, and one of them's great, and one of them kills you. How do I separate that? Well, that's another process that's very difficult. That's going to up the price, lower the yield. So if you ever wonder why is medicine so dang expensive, it's because you have to pump in a ton of money for research. Now, I'm not saying that there aren't instances of pharmaceutical companies being total bastards. I'm not saying that. I'm just saying do understand that medical research is extremely time-consuming, extremely failure-prone, extremely difficult, and extremely expensive. So, yeah, that's just a brief aside. But so Louis Pasteur, who you probably know from doing pasteurization, here's the picture. As Honey's saying, his wife is saying, "Honey, come on, it's time to go." And Louis is like, "No, I'm make my own stuff at home. Why do we need to go to the bar? It's cheaper for me to do it at home. Anyways, so he noticed that if you looked at tartaric acid crystals, which tartaric acid is in wine, so you might see these on corks, he noticed that the crystals that crystallized formed mirror images. So he's actually able to go and physically separate the crystals because they were actually, the crystals themselves actually had chirality. So he was able to resolve those enantiomers. So there's two real ways to do it. One way is to react. You can react something with an achiral compound, or with a chiral compound, and you form diastereomers, and then you can separate the diastereomers. Okay, so you have R and S butanol, and there's no way to separate those. You react it with tartaric acid, and you form two compounds that are diastereomers. Okay, and you can separate those diastereomers and then reconstitute the starting materials. So you take your inseparable compound here, R and S butanol, 2-butanol. You mix it with tartaric acid, and you get this compound and this compound. Okay, these are diastereomers. Now we can separate these, right? Because diastereomers have markedly different physical characteristics oftentimes. So then, once we separated them, then we can just reconstitute the tartaric acid and the butanol, and oh look, now I have S-butanol and R-butanol. Okay, the other way you can do it is you can put it in a column. Now you're going to look at column chromatography in one of your labs, and the basic idea is you put a column of some material, and this is the idea of all chromatography. You have some material that's going to cause some chemicals to run faster than others. And so if you have a chiral compound you have a chiral column, you can actually separate out the positive and negative enantiomers because one will run faster than the other. Because the similar enantiomer will run through fast, and the opposite enantiomer will take more time. So you can actually separate enantiomers on a column, but it's not easy. So that's chapter 5. That's, again, the hardest part about this is being able to visualize things in 3D space and remembering that when you do a Fisher projection, it reverses the assignment. Okay? So when you go to a Fisher projection, because you've brought instead of putting the hydrogen in the back, you bring it to the front, it switches the clockwise and counterclockwise. So normally it's clockwise R, counterclockwise S. In Fisher projection, it's reversed. Clockwise S, counterclockwise R. Okay, so let's look at some problems. So this is probably the one where working problem is going to be the most useful. Okay, so we're going to look at page 212, question 5-6. Okay, 5-6. Okay, star each asymmetric carbon and determine whether it has the R or S configuration. Now, I'm not going to do all of these because there's 9 of them, and I don't have all day. But so let's look. So let's just look at this. So let's look at A. You have carbon, CH3, CH2, CH3, hydrogen, terrible dashwood, and then OH. Okay, so the first thing we need to do is we need to get that hydrogen to the back. So what I'm going to do is I'm going to hold this steady and rotate him here, him there, and him up there. Okay, that's the first thing. Now I have carbon, so now on top is going to be OH. This is still CH2, CH3. The CH3 has moved down here, and now my hydrogen has moved to the back. So now I'm going to assign priority. So we look, carbon, carbon, oxygen's more important. So this is 1. Then we look carbon, carbon. Okay, that's a tie. So we look at the next thing. Hydrogen, carbon. Okay, so this is 2. This is 3. So I look 1, 2, 3. Counterclockwise, that's S. Now, if you wanted me to convert that to a Fisher projection, okay, if I were to convert that to a Fisher projection, okay, so I would want this to be on the top and this to be on the bottom. Okay, and I'm not going to do this for all of these, but let me convert this to a Fisher projection. Okay, so to make it easy for myself, I'm going to have these two coming out. So I'm basically going to be looking at it along this axis. Okay, that's how I'm looking at the molecule. So then it becomes, right, CH3 on top, and my carbon I'm looking at, and then CH2, CH3. Okay, I've got hydrogen over here, and I've got OH over here. Okay, 1, 2, 3. Counterclockwise. Oh, sorry, this is clockwise. I'm stupid. That's R. Counterclockwise in this case, so that's R because it's Fisher projection, right? That's just to show you. My brain stopped working. This is a clockwise circle, so that's R. This is a counterclockwise circle in Fisher projection, so that's R. All right, so let's look at a couple more. I'm not going to do B. That's the same as A. Okay, we're going to look at C. Okay, so in this carbon, there's actually only one chiral carbon. This carbon is not chiral because these are identical, okay? That's a CH3, that's a CH3, so you can't assign priority. But look here, however, fortunately, my hydrogen's going towards the back, so I don't need to rotate this, but I can assign priority. So we say, all right, carbon, 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 okay? So then what's next? All right, well, we go 1 over. Now remember, for this case, when you see a double bond, you consider it as though it's attached to 2 other carbons, right? That's how you consider it. So we'll say, all right, okay, so we go, so this is going to be 3. Just tell you that right now, because this is lowest priority. So these two both have other carbons. So we go carbon, and then 1, 2 carbons, okay? Then we go carbon, and we go 1, 2 carbons, okay? So then we got to go 1 over. So we go 1 over, and we get this carbon, or this carbon, doesn't matter, this carbon. And we say this is attached to hydrogen, hydrogen, carbon. This is attached to hydrogen, hydrogen. So this has higher priority, okay? Because we go over 1, we go over 1, and it's tied. We go over 2, and it's no longer tied. Okay, so that's how you work priority. You don't go here because that's a dead end. This doesn't actually exist. All right, so we'll call this 2. We'll call this 1, and we'll call this 2. Okay, so 1, 2, 3. That's clockwise. So that's R. Let's see. Oh, some of these are obnoxious. We'll do I. I has a star next to it. Why does I have a star next to it? I don't know. But let's look at I, and then we'll move on to the next problem. So question I. I've got C double bond O H, and I've got C H CH3 CH3 CH3. Then I've got C. And then I've got that nightmare. Okay? So let's think about priority. Now it should be pretty easy to see what's going to be highest priority. Okay? So we start here, we go out 1. Carbon, 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 carbon. Okay. Then we go out 2. Carbon, oxygen. Carbon, oxygen. Carbon, 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 carbon. So these are going to be lower priority than either of these two. Okay. So then we say carbon, oxygen, hydrogen, carbon, oxygen, oxygen. Okay, so that's going to be 1. Going to be 2. So now we look at these. Now remember, for purposes of priority, this is the same as saying carbon, carbon. So we say, all right, so we go out 1 and we get a carbon. This carbon is attached to 1, 2, 3 carbons. This carbon is attached to 1, 2 carbons and a hydrogen. So this actually is a higher priority. So this is already in the bag. That actually makes it easy. So then we just say, hey, yep. All right, well, that's R. And that's how you do that. So this is take practice. I recommend you go through all of those and look at them and, you know, assign chiral carbons and blah, 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 blah. And if you want to, during office hours, go over some more. I have no problem going over some more. It's the hardest thing. All right, let's see here. Page 228. Question 517. So 228.517 says, draw Fisher projections for each compound. Remember that the cross represents an asymmetric carbon atom, and the carbon chain should be along the vertical with the IUPAC numbering from top to bottom. So S-propane 1,2 diol. S-propane 1,2 diol. So diol is, so first of all, let's just draw that molecule. S-propane, so propane 1,2 diol, so diol is 2 alcohols, 1,2 diol. So the asymmetric carbon is going to be this one. Okay. So most oxidized carbon goes on top. Right, CH2OH. And at the bottom you have this H3. So 1, 2, 3, 1, 2, 3, right? So now then the question is, does the OH go here or go here? Now, we know we have to have a clockwise curve because it's got to be S, right? And this is a Fisher projection. It's got to be S. So we need it to go 1, 2, 3 like that. We know OH is going to be 1. So then what's going to be 2? Is 2 going to be here or here? Well, this is going to be higher priority than this. So if we put the, and you can like do it on one side, check, and do that, then flip it if it doesn't work, right? It's pretty easy. So we'll put the OH here, and that's 1. And then that's 2. And then that's 3. Right, this is a hydrogen. Okay, so then it goes like this, and that's S. And again, you don't overthink it, because you can throw it on this side, recognize, oh, that's R, then you just flip it to the other side, and that's the answer. Okay, so if it's wrong one way, it has to be correct the other way. So that's not bad. All right. 2 bromobutane 1-ol R. So that's A. So B, 2 bromobutane 1-ol. So we've got butane, 1, 2, 3, 4. We've got 2 bromo, 1 alcohol. Okay, so here's my chiral carbon. So we'll do, again, we're going to have CH2OH on top, and CH2, CH3 on bottom. So that's here. So 1, 2, 3, 4, 1, 2, 3, 4. Right? So now we need it to go counterclockwise. So that we are, because it's a Fisher projection. So do we need the bromine on the right, on the left? Well, again, this is going to be second. This is higher priority than this. So we want to put it so that it goes 1, 2. So it goes 1, 2 that way. We're going to put it on this side. So 1, 2, 3, counterclockwise, and that's R. Again, if you get that wrong, so it's so easy to check and correct that mistake. Don't overthink it. Don't sit here for an hour thinking, do I put it on this side or do I put it on that side? Or do I put it on this? Just put it down and see if you're right. And if you're wrong, flip it to the other side. Super easy. So don't get caught on that, deciding which side it should go on, because you put it down and you see whether that's right, and then you can flip it if it's not right. Because the only thing you'd have to do is switch these two, and it becomes the other configuration. Okay, so don't get caught on that. All right, C. S12 dibromobutane. Dibromobutane. So butane again. S12 dibromobutane. Ain't that a pretty molecule? Okay, so now on top we're going to have, I'm going to bring this over here. Now on top we're going to have, right, this is going to be 1, 2, 3, 4. So we're going to have CH2Br, CH2CH3. Okay, so then the question is, again, and we want S. So this is still higher priority than this. So my bromine's going to be over here. Okay, and again, check it. 1, 2, 3. Clockwise, that's S. And if I'm wrong, you flip it. So don't worry about it too much. In fact, you may not even, it may be easier for you to not even try to guess, to just put it down, calculate it, and then flip it if it's wrong. All right, D, 2-butan 2-ol. Okay, so now this is a little different. Because now, that goes to CH3, CH2CH3, and we got an OH, and we want R. Okay, so we want it to go this way. So this is going to have a higher priority. So in this case, the top is no longer the highest priority, the bottom is the highest priority, so I'm going to put it on this side. 1, 2, 3, anti-clockwise, that's R. Again, don't worry about how fast I'm able to identify which side it's supposed to be on. That comes with practice. And if you're wrong, you just flip it. So don't worry about how quickly I'm identifying that. If you're having trouble with that, just slap it down, see which one it is, and you know what? We're going to do that for this one. Okay. So R glyceraldehyde, and they've given us the structure. So it's OH there. So this is an OH. This is an aldehyde. Okay, so this is glyceraldehyde. So this is our only chiral carbon. So obviously we're going to have that 1, 2, 3, like that. So it's CHO. And down here you have the CH2OH. And then on this side you have, okay, so let's just throw down, I'm just going to put the OH here, and put the H here. Okay? So I'm not thinking about it, I just threw it down, and we'll see if it's right. Okay? So now we need to decide priority, this is 1. So between an alcohol and an aldehyde, right, remember this is like there's another oxygen attached to this carbon, because it's double bond. Right, so it's like this carbon is attached to 2 oxygens. This carbon's only attached to 1, so this is 2. And this is 3. But right now, the way I have it drawn is clockwise, so that's S. Is that what I wanted? No, I wanted R. So easy, right? Draw the same thing. And just flip it. Okay? So now, this is still 1. This is 2. This is 3. Now, anti-clockwise, and that's R. That's that. It's that. So, again, as long as you draw the skeleton properly, I would just throw down the stuff on the sides and see if it's right. Because it's quick. It's so easy to switch it. All you do is flip the horizontal, and you've got the other configuration. Okay, so don't get hung up on that. All right. Next problem. It's going to be page 232, question 520. For each pair, give the relationship between the 2 compounds making models will be hopeful. Okay, so 2R, 3S, 2,3 dimethylhexane. I'm only going to do 1 or 2 of these. Okay, you know what? I'm going to skip the ones that are written down. I'm just going to go to the ones that are drawn. So it's going to take forever. All right, let's look at a couple of these. So if we look at C, we've got that must be nice to be good at drawing. Something like that. That's ugly, but it'll work. Ooh, that's one of the other molecules overdrawn. Okay, so first of all, in order to compare these, I need to be able to assign both of them. So this one I can assign priorities because the hydrogen's in the back. Here, I need the hydrogen in the back. So to get the hydrogen in the back, I'm going to hold this. I'm going to rotate around this bond because that means this won't change. So I'm going to tick it over 1. So hydrogen's going where bromine is. Bromine's coming down to methane, and the methyl's going up to where the hydrogen is. Okay, so let's transform that. Okay, I'm going to do the same thing here. I'm going to hold, since this has a hydrogen in the back, I'm going to hold this bond steady, rotate around it. So this hydrogen is going to go back to that bromine. Bromine's going to go up to where the methyl is, and the methyl is going to come down to where the hydrogen is. Okay. But now I haven't changed what these compounds are, right? You can freely rotate around a single bond, unless you're in a ring. Okay, so we look at this and let's assign. Well, okay. First of all, let's look. What do we got going on here? Well, if you look at this, is this a mirror image? I don't think I'd say that it is, right? Okay, so let's assign priorities. Okay, so here, it's obviously going to be 1 for both sides, and then this is going to be 2. No, sorry, this is going to be 2. And this is going to be 3. So for this guy, it's going to go 1, 2, 3. So this is not Fisher, so that's S. Oh, no, sorry, that's R. That's clockwise. This is going to go 1, 2, 3. So that's counterclockwise. This is S. So this is S, R. Look at this one. 1, 2, and then 3. 1, 2, 3. Okay. This one's going to go 1, 2, 3. This is R. This is 1, 2, 3. This one's also R. Okay. So these SR, RR, these are diastereomers. Okay. So they're not mirror images, but they're not the same compound. Okay, let's look at F. That's the only other one I'm going to do. Actually, let's do G. Okay. And a lot of times you will see sugars or carbohydrates, simple carbohydrates, drawn out like this. Oh my God. Whoa. The world's least straight line. Okay, so if you look at these, you can see this is a mirror image. Okay, so these are most likely enantiomers. Okay, but let's go ahead and do the work, put the work in. So here, 1, 2, 3. This is S. For this guy, we've got 1, and then 2, and then 3. Okay, so 1, 2, 3. So that's counterclockwise, so that's R. This is S, R, and then 1, and 1. I think this is 2, 3. That's also R. This is S, R, R. You flip them, so they should be reversed. Okay, 1, 2, 3. Yeah, so that's now R. 1, 2, 3. That's now S. 1, 2, 3. That's now S. So there you go. So SRR, RSS, so that is indeed an enantiomer. All right. Page 244, 526. Oh my goodness. Paper's blowing away. So 244. For each structure, star any asymmetric carbons. Label each asymmetric carbon as R or S. Draw any internal mirror planes of symmetry. Label the structures chiral A, chiral. Label any mesostructures. But okay then. Again, I'm only going to do a handful of these because I can't go through all of them. Take forever. But again, if there's a specific one you want to go over, even within this problem, let me know on office hours. I can go through whatever. All right, so we look at it and we say, let's just start with A. You've got carbon, that, and like that. So first thing to do is put the hydrogen in the back. So let's hold this steady. Let's put this here, put this here, let's put this here. Okay, so hydroxide goes on the top, hydrogen goes to the back, and chlorine comes to the front. Chlorine is the heaviest, that gets 1. Then oxygen, that gets a 2. And carbon, that gets a 3. So that's counterclockwise. Yep, counterclockwise, that's S. Okay, so there's 1 carbon, it's S. There's no internal plane of symmetry. There's no mesyl compound. This is chiral. Now let's look at E. Look at E. I cannot draw straight lines. Geez. CH2Br. I've got bromine on this side, bromine on this side, and I've got hydrogen on this side, hydrogen on this side. Okay, so now these two compounds, these two carbons are chiral, so let's star them. Now let's assign priority. For this carbon, 1, and then you could go either way. Okay, now that's important. You could go either way on this one, right? So even though it's, you know what? Yeah. So wait, is that correct? Okay, so this compound is actually these are actually non-chiral because this is the same as this. Well, okay, you can consider them chiral, right? So you go carbon, 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 bromine, carbon, bromine, carbon, bromine. So you can't assign priority going this way. Carbon, bromine, and this way, carbon, bromine, carbon, bromine. Actually, no. Okay, so let me step back. You actually can. So if I go this way, I go carbon, hydrogen, hydrogen, bromine. If I go this way, I go carbon, hydrogen, carbon, bromine. Okay, so 1, 2, 3. That's counterclockwise. That's R. No, that's clockwise. So that's S. I don't know why I have such a hard time determining what's clockwise, what's counterclockwise. 2, 3. This one's going back the other way. So that's counterclockwise. That's R. But you can see you have a plane of symmetry. So this is actually a meso compound, and it's achiral. Okay, the meso compounds are a lot of times very easy to see. Now, if this had, whoa, not what I want to do. If this had a chlorine, then this would not be the case, okay? Because it wouldn't be symmetrical. Let's do one more. Okay. Let's do J. Sorry, let's do two more. Let's do J and let's do K. Okay, so J. Now, this is important because it means the hydrogen is going back. Okay. So now let's assign priority. That's obviously 1. So this is your chiral carbon. That's obviously 1. Then 2, if I go, so carbon, carbon, and carbon double bond carbon, and then regular bond carbon. So this is 2, and this is 3. So that's going to be, let's see, so that's counterclockwise. That's S, because it's not Fisher. If you look at K, then that's 1. But then we go, these are the same. These are the same. So there's no way to assign priority over here. So this is achiral. Okay? Again, this is something that if you just practice, you'll get better at it. Okay, so last problem we want to look at is page 245, question 530. Give the stereochemical relationship between each pairs of structures. Examples are same compound, structural isomers and enantiomers, diastereomers. What pairs could you theoretically separate by distillation or recrystallization? Okay. Again, I'm only going to do 2 or 3 of these. We'll just look at A. I'm sorry. Okay. Now, as you can see, these are mirror images, and they also have an internal plane of symmetry. So these are meso compounds. So these are actually the same compound. So you can't separate this one because these. Well. All right. Well, let's look at it. Okay. So I've got, yeah, but this is a meso compound. You've got this internal plane of symmetry. So, right, if you were to rotate this 180 degrees this way, you would get this compound. So these are the same compound. So same compound. So if you look at B, which is very similar to A. You notice I no longer have that plane of symmetry, right? Because on the top I would have an OH, and the bottom I have a CH2. So if I were to rotate this 180 degrees, it's no longer the same molecule. Okay? So these are mirror images, and these are these are mirror images of each other. So these are and non-superimposable enantiomers. All right, and could you separate them by distillation or recrystallization? No. No. Okay. Oops, I'm looking at the wrong problem. Do one more. Okay, do D, and then we'll call it a day. So D, look at D. You've got this compound. Oh, sorry. Dashed line, chlorine, wedge, bromine, then hydrogen, or carbon. Ooh. Bromine, I was looking away on that one. Bromine, chlorine, hydrogen, CH3. So for both of these, I need to get the hydrogen to the back. Okay. So here, what I'll do is I'll hold bromine in the front. Hydrogen will go to chlorine. Chlorine will go to methane, and methane will go, or methyl will go to hydrogen. Okay. So this one becomes. So I've got my bromine coming out towards me. Okay. Now I've got hydrogen going away from me. I've got chlorine on top, and I've got CH3 down here. For this one, I'm going to hold chlorine steady down here, and I'm going to pull bromine down to hydrogen. Hydrogen goes to methyl. Methyl goes up top. Okay, so this one. Okay, now what I can do is I can actually rotate this one more time. Right, that's perfectly fine. And so to just make it a little bit easier. Now you can do this. You can just look at priority. Okay, we can just look at priority. Oops. We just look at priority. Assign priority. Okay. Oh, where am I? There we go. 1, 2. I changed. Oh, I do not like this color. Gross. All right. So that's going to be our 1, 2, 3. That's going to be S. Now, if you were to rotate these and put CH3 here and put bromine here, or sorry, I put bromine here and then put chlorine here, you'd see that there were mirror images. Those are enantiomers. Okay, so this is going to come. So this idea of chirality is going to come into play in the next chapter when we look at some reactions that will create enantiomers or will create racemic mixtures, and you'll see that in the next lecture.